Okay, so let us start by defining the zeta function, which is the core topic we're going to be talking about. So the zeta function defined as such. Well, this is called the zeta function, and people usually misinterpret this and they think that this is the Riemann zeta function. In fact, this is not the Riemann zeta function. Well, the Riemann zeta function is the analytic continuation of this function, and it's given by the following functional equation. So the analytic continuation of this function is given by 2 to the s, pi to the s minus 1, sine of pi s over 2, gamma of 1 minus s, zeta of 1 minus s. So this is what's so-called the functional equation of the Riemann zeta function. So this is the Riemann zeta function. And people usually call this the zeta function. And the Riemann hypothesis is basically a statement about the zeros of the Riemann zeta function. But before we talk about this, let us just analyze the zeta function a bit. Well, first of all, it's good to note that the zeta function can in fact be written as the product over all primes of 1 over 1 minus p to the minus s. And for you to see this, let me give you a rough idea of why this is the case. Well, if you consider the following, this is just a hand-waving proof. And these computations were actually done by Euler. Well, if we consider the following, so if we hit this sum by 1 minus 1 over 2 to the s, which is 1 minus 1 over the first prime to the s, well, this is actually going to be something like, this sum is going to survive. This sum is going to survive. And then we're going to be subtracting the evens, the even terms. After we hit this by this thing, and we get that this should be the same sum. However, we're summing over all ends that are not even. So we omit all the even terms. So if we repeat the process, but now for the second prime, so if we get this resultant and we hit it by the quantity 1 over 1 minus 3 to the s, which is 1 minus 1 over the second prime to the s, we're going to be hitting by the quantity 1 minus 1 over 3 to the s, the following sum. After we omit all the even terms. And if we open this up, we're going to see that this is going to be the sum after we omit from it all the multiples of 3. So we're going to basically hit this by this, and we omit all the multiples of 3. And by doing that, we're going to actually get the sum 1 over n to the s. After we remove, first we're going to remove the multiples of 2 because we already didn't have these, and we're going to further remove the multiples of 3. So we're going to be left with this sum. Now, if we repeat the process for every prime, and we do that for all the primes, as such, after hitting the sum, what's going to be left is the sum, and this was conjectured by Euler. We're going to be left with the sum 1 over n to the s after removing all multiples of p for every prime p. But the only number that is not divisible by any prime is 1, and thus this sum must be just 1. Now, if we get this product and divide by it, both sides, we get that the zeta function should be actually this product for the real of zeta bigger than 1. Now, okay, and now we're about to approach the statement of the Riemann hypothesis. So stick around. So if we consider this product, let's close this. If we consider this product, which is the product 1 over 1 minus p to the minus s, and we notice that this is basically the sum, as we've just seen, which we know converges for real of s strictly bigger than 1. And we get that this product is actually an absolutely convergent product. If we consider the complex plane now, and let's say this is 1, well, an absolutely convergent product admits a 0 if and only if one of the things we're multiplying out is 0. So let me mention this. So let me state that this admits a 0 if and only if for some p, but this doesn't happen. Hence, we conclude that the zeta function cannot have zeros over here. So over here, there are no zeros. Okay, very cool. And now if we go back to the functional equation over here, and we see that if zeta doesn't admit a 0 for the real of zeta strictly bigger than 1, it cannot admit a 0 for the real of zeta strictly less than 0, except for zeros happening on the negative even integers due to the existence of the sign over here. So if we go back to the picture and see what this means that there can't be zeros over here, except for some zeros happening on the negative even integers. And these are actually called the trivial zeros of the zeta function. All of that is to say that the zeta function has its zeros in this strip, and this is what's so-called the critical strip. And the conjecture is that the zeros of the zeta function actually all lie on one line, which is the line half plus ti. And this is what's so-called the critical line. So this was actually a rough idea, and in the coming videos, we're going to be elaborating more on this. So stay tuned.